we get our water from here at UCONN?
The sewer?
No.
UConn is self-sufficient and produces its own water from the river or something.
UConn's water comes from some sort of like sanctuary or reserve for water, I'd say, because it's a pretty rural area, so we have to have some sort of like pond or something.
Where does UConn's water come from?
Local reservoir. I have no idea. The ground?
The sky? No, wait, give me a minute. I gotta think about it. Oh, you know what? There's a water place like down the road. I bet it comes from there.
There is something iconically Connecticut about the color blue. From blue laws to the UConn Huskies to, well, water. Connecticut has a rich history of being a mill state with a wonderful river system and abundant flowing waters towards Long Island Sound. But on the topic of water, not many students think about where the water flowing out of their taps, fountains, and toilets around campus comes from. Or, more importantly, where does the used wastewater go? This is where the water pollution control facilities around campus come in. Join us on our journey as we seek to reverse engineer this complicated large-scale process, from tap to bottom. The water pollution control facility for UConn is located at 25 Ledoit Road within the main UConn campus. Rebuilt in 1998, it sits on 10 acres of land. The reclaimed water facility is located right beside it, a position that allows treated wastewater to flow into the facility to be further processed for use in the cogen power plant.
These two facilities service both the main and depot campuses of UConn, as well as UConn's neighbors in the surrounding town of Mansfield. The wastewater facility processes an average 1.5 million gallons of wastewater daily. The WPCF operates under a National Pollutant Discharge Elimination System permit, issued by the Connecticut Department of Environmental Protection. Part of the water treated at the facility is released into the Willimantic River next to the Eagleville Dam. The rest goes to the reclaimed water facility.
The first stop for the collected wastewater is the headworks, located in this building here. The wastewater first runs through a step screen. This traps any inorganic waste that was carried along with the water, such as hair and sanitary napkins. The step screen brings the waste out of the water, where it is ground up in a grinder located just behind the step pier. Afterwards, the ground up material is washed to get rid of any organic matter that was trapped with it.
It's like all the crap that comes out.
What it does is, when it senses the water level getting high on the side, it'll spawn to run. Like that.
After passing through the step screen, the water is slowed to a flow of 1 foot per second. This low rate of flow encourages any additional finer bits of inorganic material, such as gravel or sand, to settle to the bottom. The bottom of this tank is sloped, funneling the material down into a tube where it is pumped upwards to the grit classifier. The grit classifier compresses the material. After enough waste has been accumulated, it falls into a wheelbarrow. The end point of this waste is landfill after it has been tested to ensure that no heavy metals and toxic chemicals are present in the mix.
This step is meant to filter out any abrasive material that may damage the pipes and tank walls, ferrying and processing the wastewater. While it does an effective job, there is also a large quantity of organic waste that is collected along with the inorganic waste. Scott, the lab technician of the facility, once ran a test to determine how much of the solid waste was organic. The test involved heating a sample of the waste to 500 degrees Fahrenheit, vaporizing the organic material. When weighed, only 15% of the matter remained, meaning that 85% of the waste disposed of at this stage was organic material.
So I'm just gonna take my grams, subtract grams of the tare weight. So we have 0.993. Divide that by 15 mils a sample. Multiply by a million. So our loss is 13,287 milligrams per liter. I'm supposed to pull this up earlier.
And what's that one?
This is a filtrate.
Okay.
What this is the dewatering machine upstairs, the Huber. The water that is removed from the sludge is called filtrate, and we test to see how much loss there is, so we can calculate how much we need to waste. Because if we say we need to waste 24,000 gallons, and we're having 2,000 milligrams per liter of filtrate loss, you can calculate how much more you need to waste to compensate for that loss. Because you're not actually removing as much from biomass from the system as you think you were.
Yeah, and how much of a sample was that from? Was that from like 25 milliliters?
That's 10 milliliters.
10 milliliters.
We've been having poor numbers recently.
Poor?
Poor.
Oh.
Five. 0, 2, 4, 8. 10 mils. That means it's 2,480 milligrams per liter loss, which is kind of a lot.
So it's not pulling as much of the biomass out? Or
Yeah,
it's
escaping. It's escaping back. Divided by your wash. 7. So we have a 19% loss on everything we're wasting.
So you have to pull out about 20% more than you predicted?
Yes. We'll have to waste 20% more.
Oh. So it's...
An interesting thing to note here is that the wastewater treatment plants normally have a primary clarifier after passing through the headworks. The primary clarifier serves to remove some of the organic waste from the wastewater to process it more efficiently. However, the wastewater that arrives at this particular facility has a lower proportion of solid organic waste per gallon than what most facilities receive, and thus doesn't need this step.
The sludge now flows to the open-air tank where the organic waste is broken down. First, a splitter box determines to which tank the sludge is flowing to, manually determined by hand-cranked valves. Just before the sludge enters the tank, magnesium hydroxide is added at this point to balance the alkalinity of the mixture. The preferred pH of the water for the bacteria to work is below 7, ideally around a pH of 6.
Each tank can hold around 1.5 million gallons of sludge. While it just looks like a very polluted river on the surface, inside there are microbes hard at work. The microorganisms consist of mostly bacteria, specifically ammonia and nitrate oxidizing bacteria, glycogen accumulating organisms, and ordinary heterotrophic bacteria. Each bacteria carries out an important function, from removing nitrogen dissolved in the water to helping break down the organic waste.
The nitrogen primarily comes in the form of ammonia. Most of the ammonia has ionized into ammonium due to the alkalinity of the water. The bacteria get to work converting the ammonium and ammonia into nitrite and nitrate. During this process, the bacteria also produce carbon dioxide, water, and more of themselves through binary fission.
This occurs in what is called the aerated zone of the tank. In these tanks, two aerators introduce oxygen gas into the water by churning the water vigorously. They operate without stopping as the biochemical oxygen demand of the bacteria dictates that they need oxygen to decompose the ammonia. Without oxygen, the microbes will undergo endogenous respiration, oxidizing their own cellular mass and consuming themselves. The sludge becomes harder to treat, not settling to the bottom of the clarification tanks because of the gas generated by the process.
Biochemical oxygen demand is measured daily to ensure that enough oxygen is being added to the water to keep the process going. In the anoxic zone, microbial flocks turn the nitrate into nitrogen gas, using the oxygen atoms in the nitrate to fuel the process. These microbes are autotrophic, pulling carbon from non-organic sources such as the carbon dioxide generated in the process prior. The CT Water Pollution Abatement Association recommends that the dissolved oxygen in the anoxic zone be lower than 1.0 milligrams per liter, but never reach 0.0 milligrams per liter.
Sludge is both introduced newly into the system and recycled back in. Multiple passes through the anoxic and aerated zones allow for the nitrogen to be almost fully processed out. An added benefit is that the long cycles allow for the bacteria to reproduce. This plant recycles its sludge for quite a while, adding up the total sludge retention time of 18 days. The end result is water that is almost up to drinking water standards, with a total suspended solid count well below EPA and state standards of 100 nephelometric turbidity units.
UCONN's bacteria to organic solids ratio is on the low side, aiming for an optimal ratio of 0.07 grams per gallon. While there is enough liquid coming in to run both aeration basins, there isn't enough food to sustain the bacteria comfortably. Thus, the facility only runs one basin and keeps a close eye whenever there is a surge of influent coming in during breakfast, lunch, and dinner.
A few years back, this used to be the opposite case. UCONN's dining halls used to grind up their food waste and flush it into the sewage system. This practice introduced more solid organic waste into the water, which forced the facility to run both tanks, leading to higher operating costs and a much higher energy bill.
During the winter and spring breaks, not a lot of waste is generated. A carbon supplement called Micro C is added to keep the microbes fed. This product, manufactured by Environmental Operating Solutions Inc., is a mix of carbon-based organic compounds. The company's website states, Micro C premium carbon sources are proprietary, eco-friendly products used by water and wastewater treatment facilities to help them achieve their contaminant removal goals. Our Micro C products are liquid chemicals generally used on a recurring basis to provide an energy source to bacteria in biological treatment systems.
The denitrification process is crucial because this water will eventually be discharged into the nearby Willimantic River, and part of it will be going to the reclaimed water facility. If excess nitrogen enters the river, it could encourage the rapid growth of algae and other aquatic plants, clogging up the waterway and disrupting the local ecosystem. When those plants inevitably die, their bodies are decomposed by bacteria, which use up the oxygen in the water and kill other plants and animals within the body of water. This would have a devastating impact on the surrounding environment and could also be potentially harmful to humans, should they go near the affected area.
If the effluent was going to be discharged into the ocean, this process wouldn't be necessary. The large volume of water in oceans would dilute the nitrogen in the effluent to negligible levels.
The facility runs this type of system because it is much less expensive than other types of systems used to denitrify and filter the water. However, the aerobic system requires a large amount of electricity to run the motors and composes most of the facility's energy costs.
This system isn't well equipped to handle the high surges of influent during the mealtime hours. When there is a large volume of water, the influent and the waste it carries has to run through the tanks faster, making it difficult to denitrify the water.
Sometimes there is a larger volume of ammonia in the water than normal. To counteract this, the gates that allow the sludge to pass through the anoxic zone are shut, giving more time for the heterotrophic microbes to process the ammonia. This leads to more nitrogen passing through as nitrate, but it's a trade-off they have to concede in order to keep the systems online and functioning.
A solution to this problem would be to install an equalization tank to hold the wastewater during the surges. Once the volume in the aerated tank hits 1.6 million gallons, the water is directed to the equalization tanks. There, the water would be aerated and held until the low flow times between 2 a.m. and 6 a.m., where it would be released into the main processing tank to counteract the low flow rates coming in. After going through a splitter box, the sludge flows into the clarifiers. Here, the solids are not encouraged to mix with the water, as the primary role of the clarifiers is to encourage the settling of sludge and other things incorporated into the water. The circular clarifiers take advantage of the different densities and physical properties of the various solids and liquids that were mixed together in the previous stage. The denser sludge containing organic matter and microbes sinks to the bottom, where it is pumped back into the aeration tanks or wasted out. The oil and lighter scum floats to the top, where the skimmers slowly push it out of the water. It then goes to the scum pump and recycled back into the system.
Only about 25% of the sludge collected at the clarifiers gets put back into the basins. The rest goes into the compressors and wasted out. Grease used to be a major issue until the dining hall kitchens implemented a program to store grease in grease tanks and not rinse down the drain. On top of the clarifiers, there might be tinning, old sludge that refuses to settle, a result of endogenous respiration. There's really no way to handle it other than limiting the process in the aeration chamber. To balance the amount of waste activated sludge and return the activated sludge, some of it is pulled out of the system, or wasted out. The amount wasted out is determined by maintaining a certain mean cell residence time, how long a single cell stays inside of the system, usually measured in days, and comparable to the sludge retention time. The amount of return activated sludge is determined by using the current plant mixed liquor suspended solids, the solid count in the wastewater, and sludge volume index, the rate that sludge is settling in the aeration chamber, and calculating how much to take out on a spot.
To compress the WAS and RAS to a manageable solid, 2 hydraulic screw presses slowly compact the material. The water squeezed out during the process is returned to the aeration basin. The compacted material is called cake, and when enough is accumulated, it falls into a dumpster. This waste is certified clean and transported to the place in Hartford where it is burned for energy.
The facility previously used a series of rollers to compress the material, but that system couldn't keep up with the volume of waste-activated sludge. It sits next to the hydraulic presses, the frame awaiting final dismantlement.
The original plan for this section had the presses dump their load within a fully automated system, wherein sensors would detect if there was enough accumulated waste and dump it onto a conveyor belt, heading straight to a dumpster. However, budgetary restrictions unfortunately forced them to scrap this plan.
After leaving the clarifiers, the wastewater is considered ready to be decontaminated. This is done through chlorination and dechlorination. Sodium hypochlorite is fed into the system using pumps, closely monitored to be as close to 0.3 milliliters per gallon. As the sodium hypochlorite hits the water, it ionizes into sodium and hypochlorite ions. The hypochlorite ion attaches to any microbes and bacteria and oxidizes them, ripping their cell walls apart, killing it. This step is important because human waste contains bacteria such as E. coli, and the treated water is going directly into the Willimantic River.
With both the chlorine contact chambers online, the water remains in the chambers for a total of 41 minutes with a flow of 3 million gallons a day. At peak flow of 7.2 million gallons a day, the detention time drops to 17 minutes. The snaking layout of the chambers allows the water to move slowly through a smaller amount of space.
Sodium bisulfite is used to neutralize the residual chlorine after the designated chlorine contact time has been fulfilled. This is an important step because chlorine is considered dangerous to the freshwater environment if the level of chlorine exceeds 0.5 milligrams per liter. Chlorine can also bind with certain carbon compounds to create a carcinogen.
After this, the effluent is now considered safe to discharge into the Willimantic River. As this is the last step in this facility, the majority of the effluent quality testing uses water drawn from here. Here they test for E. coli, ammonia, nitrate and nitrite, alkalinity, orthophosphate, phosphorus, and conductivity or salinity. If they violate any of the regulated standards, they're required to note it in the reports they sent to the Federal Environmental Protection Agency and the State Department of Environmental Protection. In addition, some of the effluent is drawn off and reused in other parts of the facility. The water used to wash down the clarifiers, the pumps, and the grinders is all recycled effluent.
The system control and data acquisition, better known as SCADA, is how the people working at the plant keep track of water flows and other measurements. It updates the information as it comes in, extending to all the lift stations in and around UCONN campus. Some of the things they keep track of are the level of nitrogen in the form of nitrate in the aeration tanks, the levels of sodium hypochlorite and sodium hydroxide in the large chemical storage tanks, the amount of water in the lift stations, and the state of pumps and any alerts that are resolved and unresolved within the last weeks. Each section of the facility has its own dedicated subsection, with the main office containing all the information each subsection collects for each.
Skate And what you want to do is, right now you're looking at the chlorine pump, the one that's on. So it's going 434.1 milliliters per minute. Your bisulfite is going 360 or 374, it just went up. And this is what's going out to the river right now, 2.3 million gallons per day. This is how many gallons per minute is going out, 1,412. If you go back to flow basin, we go back to flow basin, see this is based on 8.34 pounds per gallon of water, right here, okay? This is pounds per day they want to use. It's a figure. Million gallons per day coming in, million gallons per liter is a dose. So for the chlorine dose right now it's at 10, okay? We've had it higher than that, okay? And this is all Todd's writing. He figured this all out. 1,440 minutes per day, the equivalent to how many you want to put per hour. So you want to run 7 point, it fluctuates.
Yeah.
He's trying to keep it around 7.2 gallons per hour, okay? The bisulfite, which is over that side, they're trying to figure out that. But see, that's good and bad. And like I said earlier, and I'll show you in a second, that could change, and that will change certain times. Say if you have too much chlorine and you don't have it all being taken out, you go on this chart right here, the brain is doing now. What you're looking for is, it's not so much the chlorine, okay? You're looking at the dechlor, and that's the bottom line. That's what's going out to the river. That's the bisulfite, which, as you were saying, it takes the chlorine out, okay? So I did this yesterday, and see, I had a big hit there. So I had to be careful the next time I did it. The next time I did it, it went down a little bit, so it went down to 0. See, we get a bunch of zeros too, and we have all our paperwork going back to here. Our flow chart, look at the flow chart, the flow coming into the plant. This is what's leaving the plant. That's what's leaving down there. That's high. That's really, really high.
So you're like hitting 2 million gallons.
Almost 3. 3's at the top.
Oh wow.
3's at the top. If you go back here,
Well, lunch is coming up, so
yeah,
people are.
it's true.
Yeah.
So it fluctuates up and down. You can go on flow totals, which was yesterday was 1.5 average million gallons per day. One day was 1.993. So it fluctuates too.
So it goes from like the average is like 1.5 million ish, but it like hits like 3.
So as I was saying earlier, number 3, Rod's pump number 3.
Yeah.
It's clarifier 2, right? So here's the deal. We have it at 25%, okay? The influence coming into the plant is at 1,251 gallons per minute, okay? So you take 25% of that, it's 312.
Yeah.
So right now it's going in at 314, 316, whatever. But that's going back to the plant. So the rest of that is staying in the clarifier, or it's going over the weir, going down to the contact chamber. So that basically stays there. I was saying earlier, if we want to go to Gurleyville, okay, this are our lift stations, okay? Pump 3 is on right now. Yesterday, Gurleyville pumped 230,380 gallons to our plant. Today, they've already did 175,000 gallons.
That's high. Yeah.
I've seen this at 600,000 coming here. And you've got Store Center.
Oh, store center.
Store Center goes all the way through there. The red is on and the green is off. So we could tell right now the level, if you watch this, is going down 5.03, right? Our shut-off point is at 4.50. You keep an eye on this. When it gets down to 4.50, that would go green. And that's how we determine if we have issues or we don't have issues. So that pump 1, and we have it here alternating. So pump 1 goes on, next time pump 2 will go on.
Yeah.
So we balance our pumps that way too.
Any malfunctions within the pumps and valves and any pertinent, unusual, real-time data sounds an alarm within the system, which is relayed to the workers. This, supplemented with the daily testing within the lab, is how the facility's operators keep the sewage system up and running and how they are able to respond to any problems promptly.
UCONN's water pollution control facility is uniquely tailored to suit the campus's needs. The lack of a primary clarifier both cut down on the amount of land being used as well as helping to maintain an ideal bacteria to organic mass ratio. The biologically and mechanically based systems utilize natural processes that happen in lakes and streams all around the world. The settling of grit and the decomposition of organic matter to their fullest extent. The facility is much like a dirty river, looping back around and around until all the pollutants are suspended solids have been removed from the water.
A planned upgrade of $15 million to the facility was cut from UCONN's budget, limiting the ways in which the facility staff can respond to sudden surges in flow rates. This also calls into question how much longer the facility can sustain the growing population in the university on a system built 20 years ago. And while their systems are all well maintained and replacement parts are readily available to them, that doesn't address the fact that UCONN's growth is limited due to the amount of wastewater the facility can safely process. Wastewater treatment facilities are an important step in keeping our rivers and lakes safe for us and the plants and animals that call them their home. The Clean Drinking Water Act highlighted the danger of discharging untreated waste into the fresh bodies of water, outlining guidelines and regulations that had to be met to keep the waterways safe and toxin-free. Without this vital facility, it would be difficult to keep the natural ecosystem around UCONN healthy.
cute.
Oh my goodness. Whatever. Or I can put my face down or whatever you want to do.
Oh, I'm taking videos. You edit.